Hello, everyone. Welcome to the GeekNarrator podcast. I am your host, Kaivalya Apte, and I'm back with another very interesting episode. So, if you work with distributed systems, if you've built one, if you're working with databases, microservices, and different complicated systems, you would already know that testing those systems is really hard. And I think main concern what I have is how to gain confidence that you have tested enough, because whenever I test something, I better be confident that I have tested enough and it's good to go. But typically with distributed systems and databases and these complicated systems, it's really hard to figure out all the cases, like what you have to test, because there are a lot of unknowns. And with unknowns, I think there's lack of confidence, at least in my personal experience. So if you have faced any of these problems, you would already have heard of this deterministic simulation testing and some advanced techniques as well. But if you haven't, don't worry about it, because we have Will Wilson from Antithesis. And today we are going to talk about deterministic simulation testing, how it works, and everything around it, and Antithesis. So, welcome, Will. Thanks a lot for joining me today. And I'm really excited to have you. Let's start with a little bit of introduction about your background and what you're currently doing.
Sure. Thank you so much for having me today. So, my background is I am an engineer. These days, I don't get to write as much code as I would like to because I'm also running a business, but I do still write code every day, which is good. Keeps you in touch with what your product actually is like. So, my first role that was related to distributed systems was at a company called Foundation DB, which made a distributed database with fully serializable isolation, interactive ACID transactions, and we did that back when people were misinterpreting the CAP theorem and thought that was actually impossible. We started before the Spanner paper came out, and people literally thought it was impossible. That was very cool. I then, that company was acquired by Apple, and I worked at Apple for a little while, and I'm not allowed to talk about what I worked on, but you can probably guess it had something to do with distributed systems. Then I left Apple and I worked at Google. And at Google, I worked on Spanner. In fact, I worked on the team that was making it easy to use Spanner through Google Cloud directly, so exposing it to customers. And that was very cool. And then I left Google to start this company, Antithesis, which, as you've said, is, about we're trying to solve the problem of making software reliable and making software easy to develop, all kinds of software, but starting with distributed systems, because that is both the area that we know best and also one of the areas that's most in need of a solution right now.
Absolutely. And I am really excited to learn more. As you already said, that making things easier to test and making systems reliable. I know there are like different types of testing people are used to do. There are different layers of testing. Typically, people start with like unit testing, and then there are integration testing. And then on top of it, there are some automations written. And what I found is you always have this some input data, which is probably reading like a JSON file or some configuration, but it's all static. Like someone has manually crafted that data, and it's great, it works for many use cases. But then we also get the customer bugs that, hey, this is not working, and then there is an edge case, and probably it is already too late because you don't have the logs anymore. And I feel that it's all reactive, right? So this has been my core problem with any type of testing that I've done. And I've not done any deterministic simulation testing. I've not used any of those products. So I would love to understand the limitations, probably with the current set of testing methods that we typically end up using. And then we'll slowly try to understand what does it mean when we say deterministic simulation testing.
Okay, yeah, that's great. So you've already touched on, I think, the most important limitation of conventional testing approaches, whether that's unit testing or integration testing or whatever, which is you're always just running a test that some developer has defined, right? Some test that somebody sat down and wrote because they thought this is a situation that I should test. But that tells you right away what the problem is, right? Where are the bugs? The bugs are not in the situation that you thought of already. The bugs are in the situation that you didn't think of. And if you didn't think of it, you probably also didn't write a test, right? And so this is sort of like the catch-22 of testing. And it's why I think conventional testing is a very good strategy for catching regressions in functionality that was previously working. It can let you know if you've accidentally introduced a problem, but it's very, very bad for finding issues before they happen in the wild. And I think that this characteristic of them is made even worse in the world of distributed systems, because so many of the problems in distributed systems are related to ordering or related to failure. And and things failing in a really specific way at a really specific point in some computation. And those are just both things that human beings are very, very bad at reasoning about all the possible ways that they could happen, right? Like, imagine you've got some distributed algorithm and you've got some computer A that could fail at some moment in that algorithm. You're probably not going to sit there and write a test for each particular time that computer could fail. That's just like not really how human beings think. And so like that, I think, weakens the benefit of conventional testing for these systems. There's another issue with conventional testing, which I think is also heightened and made worse in distributed systems, which is tests are often extremely fragile because they're extremely dependent on the implementation details of the system under test. Like, you're testing that if I do some really specific set of things, I expect some really specific outcome. But there's all kinds of changes you can make to your software, which will change something not important about how that test runs, which will nevertheless make the assertion at the end fail, right? And like that fragility can happen between versions of your software or even within a version of your software. That's what we call a flaky test. And again, like this problem, it's a problem for everything, but it's extra bad for distributed systems because because they're so timing dependent, right? Because, in your test fixture or whatever, you've got 5 or 6 different virtual nodes or things, and they're communicating over some network, which has some variable latency, right? And like, it's very easy to write a test which will pass 99% of the time, but then sometimes sometimes something's a little bit slower and then it fails. And that's incredibly pernicious, because once you have a test that passes 99% of the time and fails 1% of the time, you're never going to take the failure seriously. That's just human psychology, right? And so now, I actually saw this cause a production disaster one time. Somebody made a change. I'm not going to say which company this was at. Somebody made a change, and the test correctly said that change breaks everything. But that was a very fragile test, which had some false positives. And so everybody just ignored it as usual. And then that rolled out to production and caused a big outage. So it's almost like worse. It's almost like worse to have that test than to not have it at all, right? And so this is another really serious issue with conventional approaches to testing that's made worse in this particular, problem domain. So then you asked about deterministic simulation. I think of deterministic simulation as coming from a very different heritage than the conventional sort of testing where you say, if I do the following things, I expect this to happen, right? So I don't know if you or your viewers are familiar with things like fuzzing or things like property-based testing. But we think of deterministic simulation as being more related to these techniques. So really briefly, fuzzing is an approach, from the security world where you try to find like memory vulnerabilities and crashes and other exploitable bugs by feeding random input into some system. Property-based testing is an idea that comes from the functional programming world, where you try to test like a small data structure or library by basically performing random operations on it, like through its API, right? And what these things have in common is that you are, you're not sitting there and coming up with the test and writing it and seeing what the software does and asserting some outcome. You're actually letting the computer sit there and come up with the test cases. And so then your assertions become much more general, right? Instead of like, when you do this, I expect this. Instead, your assertion is like, I always expect this property to hold, or I never expect to see this behavior, no matter what input you put in. So deterministic simulation testing, big picture, I think, is about taking that approach and that strategy of testing and applying it to distributed systems. Now, obviously, it's very, very hard to apply this to distributed systems for exactly the reason that we talked about, which is that they're highly non-deterministic, highly timing dependent. And so the idea of deterministic simulation is build some fake or virtual or mock implementation of all the parts of your system that could be non-deterministic, right? The parts that involve talking to networks or talking to disks or scheduling tasks on a multi-threaded operating system. Take all of that and virtualize that somehow, wrap that into something that you completely control. And now you can ensure that, when you feed in some input, you'll get the same behavior, you'll get the same outcome. And that's very useful for diagnosing problems. And it's also very useful for, making it possible to do this more randomized style of testing in the first place. So that, at a very high level, that's what we're talking about here. It's, I really think that if you already know what randomized testing is, deterministic simulation is not that different in spirit. It's more just like you have to do a couple of tricks to apply it to this new domain.
Absolutely. I think while you were describing the problems and the limitations of the existing testings, methodologies, I was able to recollect some of the terrible memories when it comes to terrible incidents. And I remember, again, I wouldn't also take the name of the company or the project, but we had this like async processing, and there was something simple transformations that we were doing and then persisting in a database. And then there was this test that, oh, this is happening. And it was like an automation acceptance test. And once in a while, it would just fail. And then since we didn't want to invest a lot of time in those edge cases, what we did was create like a cron job that would keep those systems in sync, do the transformation. So it solved the purpose, but again, you have to maintain like different things, different logical components, and then if things break, you have to fix them and maintain them. And the other problem with the testing or any type of testing like unit test, integration test, or any acceptance test is that you have to maintain that code. And then as soon as it breaks or you change something, you have to also update the test. And then sometimes some people also have some logic inside the test, which makes it even harder. So then they end up writing tests for tests and all of that. So it's all really time consuming and really costly when it comes to developer time. And I totally agree.
Something I didn't mention, like, I mentioned two big problems up front that conventional approaches to testing have. I think it's obvious how autonomous testing techniques, things where you have the computer generating the test cases, I think it's obvious how they help with the first one, right? Which is you're not testing the unknown unknowns, you're not testing the situations that you didn't think about testing. Like that's obvious, right? The computer's generating things for you, and so it's going to hit all kinds of stuff you never thought of. What's less obvious is it also helps with the second problem, which is the one that you just discussed. And the reason is because you're not writing, because your assertions are all about much higher level properties, right? Things that should always happen or things that should never happen. They're really assertions about like the specification of your program or the like the high level interface of your program. It's guarantees. They're not assertions about the implementation of your program, which is what many tests end up being. And the nice thing about that is that specification tends to change much more slowly than implementation does, right? Like if I have some service which I've built, which I'm providing to some customer, like I can change how that service works under the cover all the time. But usually like, what the API looks like and what the customer can assume will be true if they get a particular response, that should never change. Or if it does change, it should be behind some version flag and very carefully messaged and so on. What that means is when I write my tests in terms of that, in terms of the observable behavior, like they can also change much more slowly. So it hugely reduces the maintenance burden that you're talking about.
That does make sense. Cool. So I think I know we have like good understanding what we are going to talk about and why it is important, because that does make sense. And so let's start with understanding how it all works. Like, how do I fit all these pieces together? So let's take an example to make it more real world. So I don't know, let's say we have a chat application where we send some messages, like one-to-one messages like WhatsApp. And then there are of course, some specification like these messages should arrive in order and should not be lost, and some real basic ones. Now I have my all manual tests and acceptance tests written. I want to have deterministic simulation testing. How do I integrate this with the product I have?
Right. So I think, let's say that there's 3 major things that you have to do, and then a 4th thing that you sort of have to keep doing. And yeah, so the first thing you have to do, right, is you have to replace, like, the part of, like, you had some integration test, let's say, and your integration test like created like a little fake chat client, and it like sent like a couple of like hard-coded messages, right? Like, you still need something that's playing that role, something that is actually causing your system to do something, so that we can then make assertions about its behavior. So what we call that is the workload, right? And very often people already have something that fills this role. It might just not be in their integration test suite. It might be like a performance test suite or something. But like, you need something which is going to connect to your system and like continuously use it in some way, and ideally in some randomized way, right? So instead of like sending hard-coded messages, maybe, you send randomly generated messages with randomly generated lengths. And, that's good because now we're going to test like the chunking in your protocol, right? And, maybe you also want to do it with randomized concurrency. So sometimes there's people sending messages simultaneously, and sometimes they're in serial, right? And then, maybe you can also randomize, you could randomize the contents of the message so that sometimes they're like outside of the UTF-8 character range. Like sometimes they're sending emojis. Like now that's under, right? Like, and the cool thing here is like, this can be a very incremental process, right? You can start out with something that just looks like a hard code integration test, and you can go in and like kind of parameterize one thing after another and like make, introduce a little bit of randomness in different places. And each time you do that, you make the whole test stronger, and you actually like hugely increase the amount of code that you're covering. So that's step 1, is like have something that is performing operations against your system. So you need to do that. Then you need to answer a very important question, which is going to sound silly, but many people don't know how to answer it. And the important question is, what does my software do? Right? And many people don't know. Like, and you can sort of try and tease it out of them, and you can try and tease it out of yourself in the Socratic method. You can ask yourself questions. Should my software ever crash? Like, that might sound like a silly question, but it's actually not. There's some software that's designed to crash in certain circumstances. Should a client always be able to get a response? Should they always be able to get a response after some amount of time? Should they always be able to get a response if at least 1 or 2 or however many things are up? Should the messages always come in order, like you said? Should a message always be durable if the client has gotten back an answer saying, okay, I've sent this? Should messages ever be duplicated? Or like, even with a very simple chat app, there's actually a lot of questions and a lot of potential things which might be true about your system. Again, what's very powerful about this, and this is not intuitive, but this is like, I think, one of the most important things for why this whole style of testing works really well. You don't need to have a perfect answer to all these questions. Like, often you don't even, like, the crazy thing about bugs, okay, and this is true if you just think about how software works, right? Like, your software has some invariance inside it. Like, there's some assumptions that your software makes. Once one of those assumptions gets violated, very frequently all bets are off. And so what that means is, one bug in your software will often produce many different possible symptoms, right? Like, if there's some consistency bug in your chat application, maybe that sometimes results in duplicated messages. Sometimes it results in messages out of order. Sometimes it results in your application crashing. Sometimes it results in, right? Like, it could like have a huge number of things. And so now that's great because I can find that bug just by adding one of those properties, right? And I don't need to actually have them all. It's better if I have them all. I'll find bugs faster. I'll find more of them. But I can get started very simply just with a few kinds of assertions about the behavior of the system with this randomized workload. Okay, so I've got those 2 things. Now comes sort of the hard part. And this is, I guess, like, I don't want to turn this into an advertisement. This is the part that Antithesis does actually help with. So The next thing you need to do is you need to make it so that your implementation of things like networking, things like task scheduling, things like fault injection, make all those things deterministic by not relying on the operating system to do those things, but instead having some in-process or user space library that you can use to do virtual versions of all these things, right? So, for example, your real chat application might be a client and a server, or a client, many clients and many servers, which are deployed with Kubernetes, in AWS, and talking over real network connections, right? But if we tried to test it like that, we wouldn't get anywhere, because we would try doing some randomized thing, and something would go wrong, and then you'd never be able to get that failure to repeat, because it depended on very precise timings of what ran when, right? And so you need to then take this whole service topology that you've got, and you've got to kind of simulate it, right? This is where the simulation part comes in. You need to replace it with like something that you can actually make do the same thing every time. Maybe you run the client and the server as, separate green threads or tasks within a single process, and you control their scheduling directly. You have a virtualized network implementation, which is maybe like some local in-memory buffer that you copy packets into, and then you copy them back out on the other side. Like you've mentioned a couple of practitioners of simulation testing. They all actually have different approaches to this. And I think there's like a couple of libraries now that can help you with some of this stuff, but I would still say this is the most like kind of annoying part of the whole thing, is like getting a good deterministic simulation. So that's one of the things that Antithesis tries to help with. We actually have written a hypervisor, right? So rather than having to reach in and like change how your software works to make it deterministic, we just like wrap it all and force it to be deterministic by running it on a deterministic computer. And that lets you do this style of testing without really changing anything about how you deploy your software, which eliminates that problem. So then there's a fourth thing, which I alluded to as a thing that you have to sort of keep on doing. And this is actually, I think, the very hardest thing. And it's also something that our company can help with. And that's like, you need to keep asking yourself the question, is this helping me find bugs? Is this finding all of my bugs? Like, are any bugs making it through? Because the thing is, like, the state space of your software, like all the possible things it could do, it's like basically infinitely large. And so there's no testing system that can try all the possibilities, right? And so you need to construct all the sources of randomness I mentioned, both the randomness in your workload or in your inputs, and also the randomness that you're injecting into the environment on purpose to see what happens. All of that needs to be designed to sort of explore the interesting parts of your software and not the boring parts, right? Like, so what's interesting and what's boring? Like, imagine your chat application and the network is always 100% perfectly good, right? Then there's like never any leader election. There's like never any possible durability violation because some write got acknowledged before it was done or whatever. Like, that's pretty boring. Like, if we ran that test for years and years, it would never find a bug, or at least not find a bug in the distributed systems part. Or you could like continuously have everything be disconnected, right? And like that would also not find very many bugs because none of the messages would make it through, right? So there's like some in-between point where you're dropping just the right number of packets and disrupting just the right amount of activity where you actually get lots of interesting behavior. But finding that point is actually a rather tricky empirical challenge. Like, you may need to try many different random number distributions for when you drop things and when you interrupt things. And the same applies to like, how many emojis should I put in this message versus how many normal characters, right? And figuring that out and refining it and keeping it up to date as your software develops and changes can actually be a little bit of a tall order. And I think this is the other really big barrier to people doing this kind of testing themselves, And so that is also something that Antithesis tries to really help with. We use a bunch of techniques from machine learning and also from like good old fashioned 1980s AI, some heuristic research to try and tune these distributions for you so that you don't have to think about that question, so that your tests do actually just find your bugs without you having to put a ton of intelligence into them, because the intelligence is coming from our platform. All you kind of need to do is let us know what levers we can pull, like what we can do to your software, and it figures out the rest. So, sorry, that was a very long answer to your question, but I would say like those are the four sort of main categories of stuff you have to do, and like our goal is to do two of them for you.
No, I think it does make sense, and thanks for the detailed answer. So if I understand correctly, so like I write any other test, like a unit test, I have to generate some input, and that's when I should know how to pass in those inputs to my system, and I should have some clients or something like some kind of worker that does that. And then the other one is I need to know my specification. What do I want from my system? Like the messages should be in order. No message should be lost. There should be like at least one guarantees or exactly once delivery guarantees and all those things. And then there are basic test cases like what happens when I send a message that is longer than, I don't know, some length, or what happens if I just attach a very large file and then that file is split into chunks and all chunks should be delivered and all of that kind of stuff. So there are different types of expectations that I have. There are functional requirements, of course, there are non-functional requirements. Then there is the latency part, like how quickly should I be able to deliver the message and all of that. How do I define that? What kind of language do I use to specify this to Antithesis?
Yeah. So basically, we divide the world into two main kinds of properties. Okay. There's always properties, which are things that should always be true of your code. And the always of a negative is obviously a never. So there's always and never properties, which are the same kind of thing. And that's the kind of thing that most assertions that most developers are familiar with are, right? Like you can write an always assertion in, any language's assertion framework. That's like a very common thing. And so we support those too. And that's like a very important part of simulation testing and of autonomous testing more generally, right? Like, my thing always gives an answer. My program never crashes. Like it's like very natural to have these kinds of things. Then there's sort of the opposite. And this is the one that I think is much more confusing to people initially, because you don't see them really outside of simulation and autonomous testing. And these are like sometimes properties, right? So sometimes the file is so large that it gets split across chunks. Sometimes the message does not fit, with the Latin 1 character set. Sometimes a leader election occurs and the service is able to continue. So, okay, why do we care about these properties? This is like very strange, right? Like, if it's a sometimes thing, then like if I make it succeed, then fine. But if I make it fail, like that's not necessarily a failure. Like it might just not have succeeded yet. I might just need to like keep making it happen. So the reason these things are valuable, there's actually three reasons these things are valuable. One is that they give you a lot of information about how effective your test system is, right? This is like, you can think of these things as like a generalization of the notion of code coverage, right? It's more like behavior coverage. You want to know that your test system is capable of creating the situation where some particular event has occurred. Like asserting that sometimes that occurs, like will tell you whether that's true or not, right? And so it's like, these are like sort of assertions about the test themselves in this sense. That said, they can also catch very real bugs, like reachability or, being able to get in a particular situation is actually a property of your system, which could actually be broken by a code change, right? Like imagine I'm developing an e-commerce website and I want to say sometimes it's possible to complete the checkout flow, right? Like, it's not that every path through my website will complete the checkout, but like it should be possible to complete the checkout. If it isn't, then there's a real bug there, right? Or, imagine I'm developing a computer game and I'm like, look, sometimes it's possible to get to every level. You don't always get to every level. You can also die, right? But like, it should be possible to get to every level. And if it's not, then that's actually a real bug in my computer game. So that's the second reason these things are important, is they can actually help you find real bugs. Then the third thing that they're very useful for is basically guiding this randomized search. So this is something that's like a little bit more unique to Antithesis, I think. But remember I said that like it's very hard, it can be very hard to know that all of your random distributions are correctly calibrated to actually explore your software very effectively, right? So one way around that is you can just make the problem less hard by noticing when you've caused some situation to occur and then like continuing testing from that point more often, right? Let me give you a concrete example here. Let's suppose you have your chat application and it's got some master server and there's some leader election process that results in picking a new one of those. And you know that is like a sometimes buggy process, right? So it would be very nice if you could, like, imagine it's hard to get that leader election to happen. It would be like maybe only 1 in 1,000 test inputs cause that leader election to happen. It would be very nice, though, if more than 1 in 1,000 of your testing energy, of the CPU cycles that you spent on testing, were testing like stuff downstream of that leader election process. And so the nice thing about deterministic simulation, because it's deterministic, once you have an input that gets to that leader election, once your current testing run has found one of those, you can just replay that input and then do more stuff from that point onwards. And so you could say, right, like, okay, if I see this message, like beginning leader election, I'm now going to spend half of all my energy, like just replaying up to that point and then doing further testing. And then the other half, I'll just, be testing from scratch like normal. Great. Like that will hugely increase coverage of that particular path and might find a lot more bugs. Well, now the question is, how do I automatically know? How do I determine which things like are interesting in this sense, right? And one way is to have a human being tell you. And the nice thing about these sometimes assertions is they're a way for a human being to tell you this information without having to do any extra work, right? You have already said to me that you care if sometimes I generate messages which are large enough that they get split on chunks. Like you care so much, you've written an assertion to see if the test system is doing that. Okay, well now the test system can just be like, he obviously cares. So I'm going to make sure that when I do get to this situation, I do more testing from this point onwards. And I, put more energy into this situation because it's something that a human being told me was important. So that's like, that's the other style of assertion that you can do. And they're also very, very valuable. As to how you write these assertions in our system, which was your first question, there's a lot of ways. Like we offer an SDK that allows you to write these things very directly in your code. That's really easy. We also store all of the output of your system in all of the many, many runs we do through it in like a giant analytic database. And you can then sort of write, the same way that people do log spelunking in big observability systems like Datadog or whatever, you can do that in Antithesis, but you're doing it in like a mirror universe where your customers haven't hit the problem yet, right? And so you can just sort of go hunting for error messages in all of the output of your system. And then if you find ones, you can then convert those to actual programmatic assertions in the future. There's a bunch of other ways as well. We can hook into your existing error reporting mechanisms or, parse your log files or whatever. And you can sort of define assertions over those things. There's quite a lot of options.
Okay. Sounds very good. And thanks for sticking to the chat application example because it makes understanding a bit more easier. Let's talk about the third layer though, like when, or the third step, when you said you have this hypervisor that you have created and that helps ensuring determinism without actually making some changes in the application, right?
Yes.
So, how does that work? What is the input to that hypervisor? And is it like my Docker image or something else? Or how does that work?
Right. So this is a good question. So the hypervisor is a piece of software that runs a VM fundamentally.
Mm-hmm.
So under the covers, what's happening when you provide your software to Antithesis? So our customers provide their software in the form of one or more Docker images, basically, plus some description of how they connect to each other. That could be like a Helm chart or a Docker Compose file or whatever. So what we're then doing behind the scenes is we're taking these Docker images and we're like burning them onto a live CD. And this is all happening virtually, right? And then that live CD is being put in the like virtual CD-ROM drive of this VM, and it's booting from it. And so the hypervisor, so the hypervisor has baked inside of it all of your software, plus like outside of your software, running those containers, a Linux operating system with a kernel version that you can configure and various other stuff that you can configure. And so then we run your software in this simulation of an actual distributed network, right? The computers are just containers, and the network connections between them are just like local container networking inside of this VM, inside of the hypervisor. The hypervisor then has this challenging task and needs to make it so that execution of that system, if we feed it the exact same input, will do the exact same thing. And that's true like down to the CPU instruction on the timings. That's true about the order of every thread execution. That's true about what answer you could possibly have gotten from a random number generator. And making all of that work and making it work fast is actually somewhat challenging. We have a blog post on our website by one of my colleagues, Alex, about the sort of big picture of how the hypervisor is designed and how it makes those things work. And I encourage you guys to go read it. I'm also happy to explain more of the details if you want. I should say the hypervisor has one other goal, which is also quite challenging, which is it needs to remember we're doing autonomous testing here. We're doing simulation testing. And so we want to not just run your system once, right? We want to run it many, many, many thousands of times very quickly. And we want to like see if we can cause it to break by doing different things to it in different situations. It would be very slow if we sort of had to like boot up the hypervisor and load your software and hit go and wait for it to do something every time. And so you obviously want to be able to snapshot it at the start of a test, right? But then if you think about it, hang on a second, I actually want to snapshot it all the time, right? Like go back to the example we just had of the leader election. Like if I'm going to fork off lots of testing from that point, well, I want to be able to snapshot it right there. Like that would be much faster. Then I wouldn't have to replay the part of the test that gets me to the leader election every single time. That could save a huge amount of time. Okay, well, so I want to be able to snapshot tons and tons, but this hypervisor is running on one computer, right? Which has a lot of memory. It's a very big computer, but it's still like a finite amount of memory, and it has a lot of CPUs too. And so we could be doing many of these tests like in parallel, and all these VMs are using memory. And by the way, we're also snapshotting them. Like this sounds very inefficient. And so our hypervisor has one other pretty cool design feature, which is whenever you fork the VM, right, or take a snapshot, we only make copies of the memory pages that have actually been modified in that particular test run. So, if I snapshot your system and then I try two different possibilities from that point, it doesn't double the memory being used at all. Like the vast majority of the memory is actually shared by the two VMs. They can't see it. They don't know that the other one is there, but they're like both accessing the same raw underlying physical pages. And so that hugely increases the parallelism that we can use when testing people's software, which means that we find bugs faster, which makes people happier. So that's like another kind of interesting property of this hypervisor. And it's like a little bit, you won't find that on our website anywhere, but it's actually very important.
Interesting. So I imagine it's like a tree, like you're branching out different possibilities, like what can happen. But you only snapshot the memory pages that have changed, and that reduces the snapshotting cost basically, and the amount of data that you need to store.
That's right. And it reduces the snapshotting time, makes it very
Yeah.
fast operation too.
Okay. Because speed is really important, right? And I wanted to understand this as well. While just to take a step back and just repeat what we have been talking about. So I have this, let's say I have my code base, I just make changes and there's some CI/CD pipeline and I create these Docker images. And then something triggers Antithesis to start running all these tests. But continuously, I'm also changing my code base and making some more changes. So how is that isolation taken care? What version of software is breaking and what version is not?
Right. Great question. So basically the way this works today is so this sort of like factors into our pricing. Like basically the way that our pricing works is it's usage based. It's just like EC2. Like you pay for the amount of computers that we're running. And so like, I don't know, suppose that you're running 10 computers, right? Like we can use those 10 computers to all test the same version of your software, which you just sent to us. And then we'll find bugs, 10 times faster than if we use one computer. It's a very parallel problem. Or we can use one computer to test each of the last 10 versions that you push to us, right? That would also be valid. Or maybe you want to use 5 computers to test the most recent version and 5 of them to test the version that's currently running in production, or right? Like there's sort of a lot of choices here. And basically, we do think there are some common patterns to how people want to do this. But at the end of the day, this is like kind of up to you. Like you can, we provide a webhook that lets you tell us like, hey, I've created a new version of the software, like start running on this. And like, but there's a lot of sort of parameterization and stuff that you can do to decide which versions you want to run on, how often and how much. One current limitation of our platform, which is a very temporary limitation, I hope, is that like startup latency is non-trivial, right? So it takes like maybe 5 to 10 minutes just to start running a test. And we have lots of plans for how we're going to get that down into the like seconds range. But right now it takes 5 to 10 minutes. And so what that means is like, you're paying for that 5 to 10 minutes of the machine booting, right? And so that sort of biases people towards running fewer, longer tests, which, yeah, there's good things about that and bad things about that, right? The good thing is like a longer test may get deeper into your system, may find a rarer bug. If it's a bug that requires you to actually do a number of very difficult or specific things in a row. But it's obviously less good because it's higher latency to knowing that you have a bug if it were a shallow bug, right? If it was an easy bug. You would prefer to run that test on every single version of your software and find that bug right away. So, so that's a trade-off. Right now, that trade-off is not really a thing that people can control directly. It's like, so we're pretty biased towards longer tests, but that's something that we plan to fix pretty soon.
Okay. Interesting. That makes sense. And again, I guess it's a trade-off that you want to catch bugs quickly, or you want to run the same version 10 times, or you want to run 10 versions differently. I would imagine that it would be something like, let's say I've been running this test on one version, and then I don't know how much time does it take, because the problem space itself is pretty, let's say, random, because things are happening, and then it can really grow like exponentially depending on the complexity of my logic and the systems or components involved. So how much time does it take? Like, how do I know that, okay, I have covered everything in this problem space and it's time for me to end the test and give a report?
Right. So the best way to know that you've reached the coverage that you're expecting is with these sometimes assertions, right? if you've designated in your code all of the sort of tricky situations that you think are very important to cover, and if the test suite gets to a point where it's like succeeded in making all those situations happen, then like you can be pretty confident that the test has like actually tested a bunch of stuff. As to how fast these things run, like it's really, that part is really, really under your control. Like, and this is also a part that like people can put some work into, and it will hugely improve your experience of doing this style of testing. So like at FoundationDB, we very aggressively tuned our database so that the simulation testing could happen really fast. And I would say we found the vast majority of bugs within like a few minutes, and there's a lot of tricks that you can do a lot of pretty basic tricks actually, right? Like here's a really basic trick. Like whatever property you think you have, or whatever, invariant you're trying to validate, like validate it continuously. Don't wait until the very end of the test, right? So like if you're, if you've got a chat application and you're sending messages, and then, you want to check at the end that like all the messages were received, don't just check at the end. Check like, every 10 seconds or every 5 seconds that like all the messages that should have been received up to this point have been received and there's no gaps. Like, and then if there is a problem, like throw an assertion or throw an exception right away, like right in that moment. Like that way we don't have to trade off like how long this test could possibly run versus, getting quick feedback and quick latency on problems that are found. So that's like a very helpful idea to have in mind. The other benefit of that, by the way, is that there are bugs. Sometimes like two bugs can cancel each other out, right? Or sometimes like, there's a bug in your system, it gets into some bad state, and then some later fault injection, let's say, restarts that node, and now the bug is no longer there, right? Like checking continuously or checking more often than just at the very end of the test means that you would actually find that bug where, otherwise you wouldn't have. So that's another reason to do it.
Interesting. Let's go a little bit deeper in how like different test cases are identified and making sure that we have enough coverage. So how does that, if you can share some, I don't know, some internal algorithms that are used, or some general algorithms that are used that are pretty common and viewers would be interested in reading more on this.
So what specifically are you referring to here? Like there's, so let's go back to your metaphor of the tree, right? Yeah. There's like a tree of all possible program states.
Yeah.
This tree is like infinitely huge, right? So yeah. we know that we will never, ever, ever be able to get to every possible leaf of this tree. Mm-hmm. But we want to feel good that the infinitesimal fraction of it that we have explored is in some sense very representative of the whole tree, or, or covers most of the likely failure cases, right? And so is your question, how do we know we've done that? Or is your question like, what is our strategy for exploring this tree that gets us to that outcome?
Yes, I think the latter, like the strategy used.
Yep, great. So yeah, so this is great. So this problem then, again, using the metaphor of the tree, we can say it breaks down into two sub-problems, okay? And our internal jargon for these sub-problems are tactics and strategy. So the tactics question is, given that I am currently at this node of the tree, okay, what do I do next, right? Like I have many choices available to me. If it's a chat app, right, I could send a big message. I could send a small message. I could slow down the network, right, with fault injection. I could cause some node to restart. I could, change the order in which the workload does. Like, I have a bunch of options available to me. Which one do I do now? Obviously, very important question. Very hard to figure that out in perfect generality. And then the strategy question is like, I have this whole tree, which node should I start from, right? Which node should I put a little bit more effort into investigating or trying something from? And that's also a very hard question. And in general, okay, we can say a few very big picture things. First of all, if I had a perfect solution to either of these problems, I wouldn't need to solve the other one, right? Like if I always know what the next thing I should do is, then I don't have to worry about where I'm standing because I'm always standing in the right place. And if I always know where I should stand next, then I don't need to worry about what I'm doing. I just do breadth first search or depth, and I like see which one's the right answer, and then I go there and then I try everything and see which one's the right answer, right? So if I had a perfect solution to either one, I wouldn't need the other one. Okay, that's the good news. The bad news is it's impossible to have a perfect solution to either one because it's the Turing halting problem, right? If you had a perfect solution to either one of these, you could find all the bugs, and obviously you can't do that. Okay, so given that, I'm gonna want to invest a little bit in both. And the good news is that there's actually very, very, very broad classes of heuristics which work very well for a very wide sample of programs. And getting into the really low level details here is like getting a little bit into trade secrets, but I will try to sketch out like our process for how we figured this out. So, one thing that's very important, which is an idea that we took from the open source world of fuzzing, actually. The most famous of the coverage guided fuzzers, the one that sort of started the coverage guided fuzzing revolution, was a system called AFL. I don't know if you've heard of it, but it's very commonly used by security people to test software. And I think the brilliant thing that AFL did was just approach this question as a science problem. So they got hundreds of programs, all different kinds, parsers, image libraries, browser rendering engines, compilers, simple computer games, all kinds of stuff. And they just ran their test system on all of them. And then every time they thought about making a little change, they would measure its effect on this incredibly broad sample of programs. And by doing that, they've empirically found some common laws which applied across all of them, which were very, very powerful and very general. I'll give you a silly example. When AFL is generating an input to feed into your software, right? So AFL's model of the world is it's feeding an undifferentiated byte stream into your software, and your software can choose to interpret it however it wants, right? So one of the tactics of AFL, one of the things it can do, is go back to some point in this byte stream and change what the byte that it put there was, and then see if your software does something different, right? But when they change it, they don't change it with uniform probability. They have hard-coded in AFL an array that you can see in the source code. It's called list of interesting numbers. And what are the interesting numbers? The interesting numbers are 0, 1, 2, 3, 4, 7, 8, 2 to the 32 minus 1. They've got a few thousand numbers there, and they found that those few thousand numbers are find 99% of the most interesting behavior in any software program, even, despite being a tiny, tiny fraction of the total space of numbers. So that's, but the meta technique here is, I think, the more important part, right? The important part is not that list of numbers. And maybe that list of numbers doesn't actually work for distributed databases or something. The important part is you have a very large set of very different programs, and you're looking for things that improve your performance or improve your ability to find bugs across all of these programs. Because once you found things like that, makes it much more likely that the next program that comes along, it will improve that too. It makes it less likely that you're overfitting on the particular programs that you started with. other very common techniques used by autonomous testing systems. I mean, looking for novelty is a key one, right? Looking for new things. So if you look at AFL, again, it's open source. Go look at it. It cares a lot about finding new code. That's obviously a very good guideline, right? If I make some new line of code, if I'm exploring the tree and I get to some new leaf, or I get to some new node in this tree, and when I get here, your program runs a line of code that's never run before, that's like a very good suggestion that I should start from this point when I want to explore in the future. It's not a perfect guideline, by the way. Sometimes new code is actually bad for finding bugs, right? Imagine the code that's like, I'm deleting all the keys in the database. Like, very possibly, like, when you run that code, like, it hides bugs, which you've already turned up. And so this is not a perfect guideline, but it's a pretty good heuristic. Going around loops more times, like, often means that you are going to get to some new behavior that you wouldn't have gotten to before. There's like lots of stuff like this. We've tried to generalize beyond just like the code coverage type stuff. Like, often behavior of your program is very important, right? Log messages that it produces, that can be a signpost to some, you've made something happen that you haven't made happen before. Again, there's subtlety here though. There's hard parts, right? Like if your log messages contain timestamps, like, then it's very, very easy for a testing system to generate an infinite diversity of log messages just by waiting different amounts of time and then causing the same log message to get printed out. So you need to be able to somehow recognize that some part of the log message is actually just a high entropy source of noise and then ignore that, right? That's actually quite challenging. This is related to a problem in machine learning called the noisy TV problem, which is that if you have any agent that's seeking diversity or novelty in the environment, it can get attracted to just a pure source of noise and fixate on that, right? So that problem actually comes into the autonomous testing world, which is quite interesting. And you need some way of dealing with that. Like, I could talk about this topic for hours. Sorry. Suffice it to say, it's very hard.
Yeah. Thanks for the references, and I'll probably add those links so people can review it. And it's definitely an interesting and probably seemingly complicated problem to solve. I still want to ask you probably a naive question, going back to my metaphor of this tree. When I'm on a particular node, do I have to also keep the historical context, like what path I have taken? Because then probably it is possible that I might end up in an infinite loop that I try to create the same case again and again without having the historical context. And I just keep testing the same type of failure and keep visiting the same nodes, basically. So how is that handled? And is it part of the snapshot that is taken?
So I want to understand the concern a little bit better. The idea is, if I don't remember how I got somewhere, then I could basically always end up starting from some ancestor of that place and then doing the same actions over and over and over again.
Yeah.
Right. So basically, you're absolutely right. That's theoretically possible. The thing is, like, if your testing system is doing that, then it you're absolutely right. You could defend against that in various ways. But if it's even a possibility or a likelihood that your testing system is doing that, it's probably not a very good testing system, because it's very biased to doing a particular source of activities, right? Basically, like, imagine that your testing system is completely random, right? So let's think of our tree as being indexed, the height, right, by the number of bytes of input I've put into the program so far, right? And so I've got branching factor 256. After I feed 1 byte of input into your program, there's 256 possibilities, right? After I feed 2 bytes of input into your program, there's 65,536. After I feed 3 bytes in, there's 256 cubed, which I don't know off the top of my head, right? Like, so like, even a very, very short input is like quickly going to lead to like billions and billions and billions of possibilities. So if whatever approach to exploring this tree I have ends up hitting the same possibility over and over and over again, it can only do that if it's like outlandishly biased towards taking particular kinds of actions, which means it's probably not very good at exploring all the possible things your software can do. Like, basically the concern, like, you've raised a valid concern. And what I'm telling you is, long before we get to the situation you've described, our testing system is already totally broken and not useful because it's basically just doing the same thing.
Okay. So probably it's biased, and that's why it is not covering the entire tree, but it is more going towards one branch of it and ending up on the same situation.
Right, that's right. Like a good testing system is going to do a mixture of stuff that it thinks has a high probability of finding problems and stuff that's like just completely random. Because like sometimes you're wrong about what has a high probability of finding problems. And so you want to mix in some randomness while you're going all the time just to sort of check your assumptions.
Okay. That makes sense. Cool. I think you mentioned about mocking, right? Because let's say I have my chat application and there are, of course, some different components involved. Some components are in my control. Some of them, let's say, are external, like third-party callers. Just to extend on the chat application, let's say I want to understand what the intent of the message is, and I want to make sure that message is not hurting some sentiments or it's not abusive or some fake information and all of that. So I hit a third-party API that gives me this intent, and then based on that, I try to filter and give some warnings probably. How does that mocking work, and what is the expectation from let's say from me as a developer, for you to be able to mock that behavior?
Great question. I would say this is one of the current highest friction things about deterministic simulation testing, whether you're doing it in our platform or you're doing it some other way. Whatever approach you take here is going to run. It's not impossible. It's just like going to be annoying. So, suppose that you're doing this by yourself, right? And you've developed your own virtual deterministic implementations of, network communication and so on. It's very likely that whatever third-party API you're connecting to or hitting is non-deterministic in some subtle way, right? It gives slightly different answers at different times of day. It can take different amounts of time to give you an answer, right? Like, there's a very good chance it's going to break what you thought you had. You might have some chance of fixing it if you could run it yourself, like if it was open source or otherwise somehow under your control. But if it's off there sitting on the internet somewhere, then you're really in trouble. And yes, like when you want to test against the system yourself, like you need to have some kind of mock. So all of that is also true in our platform, with a couple of things that make it slightly easier. Oh, this is still a challenge. First of all, if the thing is not open source, but you can run it, like you can download it and run it, then there's no problem, right? You just download it and give it to us, and we'll run it next to your software, and it'll do whatever mysterious thing it does, but it'll do it the same way every single time because it's running in a deterministic environment, right? There's nothing it can do to stop our hypervisor from being deterministic. So that's good. If it's a third-party service that you cannot control and cannot run yourself, but they're also already our customer, then again, you have no problem, and we can just automatically connect your things together and test them together, and the resulting thing will be deterministic. There's also a number of high-quality mocks that we've actually written for things that almost everybody uses. For example, AWS, right? Like, so we have like fake AWS endpoints that run in our simulation that work quite well. Like we use them for our own testing. And, we've got a number of other things like that we've developed. But in general, like this is still a problem. And it's a problem, it's a problem inside our platform just as much as it is outside. If you're depending on something that you cannot run yourself, and maybe isn't super common, so there's not some existing open source mock that you can download and use, and in the case of testing with us, it's not one of our other customers, then you do need to sit down and write a mock yourself. And that, depending on what your goals are, that could be either really, really annoying or not a huge deal, right? If you just need the mock to answer okay every time, and then great, it's not so bad, right? If the mock needs to maintain some complicated internal state so that later you can issue queries against it, and by the way, it parses your SQL, and that could get very hard. So this is absolutely a thing to worry about, and I think it is probably the highest friction part of simulation testing today.
Okay, that makes sense. One other case that was coming to my mind, specifically this chat application, and I use WhatsApp. So there are these, I would end up in a situation where I have to test for a state that happens after a long time, for example, 24 hours, that I send a message and this message is disappearing message. So as soon as, I don't know, 24 hours has passed, this message should automatically be deleted. It was never sent or something. So what kind of, thing or feature we have there?
Super common situation. Yeah. So I have two answers to this. The first one is one that everybody should do all the time, which is these things should be parameterized. And then you should set the parameters to values that will make it so the situation gets hit more commonly in your test than in production. And by the way, actually the best, most advanced thing to do is to randomize the parameter, right? Because that way you test even more situations. So you're disappearing messages after 24 hours. Let's make them instead disappear after 5 seconds, or maybe sometimes make them disappear after 5 seconds, and sometimes after 5 minutes, and sometimes after 5 hours. And now we will be hitting all those situations. And this happens in many, many other contexts, right? There's often parameters that have one optimal value in production for efficiency reasons or whatever, but in test you want to set them to a very different value to make some interesting case get hit more often. So that's very important. The other thing, which is true of our system and true of many other systems as well, is that if you have a deterministic simulation that's event-based with a virtualized source of time, you can just always you can sort of fast forward through the simulation if your software is mostly idle, right? So you can always just skip ahead to the next event that would happen, right? And this is something that our platform implements. It's something that many, many other people who've built deterministic simulation have implemented. If nothing is happening in the system, just skip the clock forward until something happens again. And that way you can actually run through much more simulated time in a shorter amount of real time and hit more of these situations. And I think that's especially applicable to testing distributed systems, which are often relatively lightly loaded, but events do actually take time to play out.
Okay. Yeah, that is a very common use case. And probably even in the integration test or acceptance test world, we try to simulate that using different parameters. So I think that should be applicable in this case as well. In the interest of time, let's move a little bit higher level again. I want to ask you, so of course there can be different classes of bugs, right? One, for example, data loss, there is security incident, or there is some just latency spike or different types of issues. And these issues maybe have different importance for me. So does Antithesis gives me the ability to first classify the error, what kind of error it is and what component is causing this. And then the second one, how important and what is the risk and what is the importance that will help me prioritize the fix for this bug.
Yeah. So the most basic forms of triaging that we can do for a bug like this are, number one, we can tell you what kind of test property was violated, right? And you've hopefully, labeled your test properties in some sensible way, right? Like, maybe this bug caused a service to crash, and this other bug, caused latency to go up beyond the level that you said was acceptable. And then this third bug over here, like, caused somebody to be able to read data that was not their own, right? Like, and that violates some assertion. Those bugs could have very, very different priority levels for you. And, and by the way, like, it's not always obvious. Like, they could have different companies could assign different importances, right? Like, we sort of shared a smile. Like, obviously the confidentiality violation seems like the most dangerous one, but like, no, if you're making a pacemaker, maybe the service crashing is really more important. And if you're making a high frequency trading system, maybe the latency spike is actually the most important, right? So like, different people are going to care more about different things, and our platform will tell you like what problem it was that it found and in what component and so on. Another thing that we can tell you is how easy was it to cause the problem to happen? Like, did we only find this bug after hours and hours and hours of searching? Or did we find this bug like right after we turned on your system? Or, and do we find this bug in every version of your system, or is it kind of intermittent? Like, there's information, like, it's not foolproof to translate this into real world probability. Because of course, if our system was perfect, it would find every bug right away every time, right? And so to the extent that it cannot do that, it could be because the bug is really hard to find, or it could be because the bug is, for some reason to do with our system not being perfect, right on the edge of what it can find, right? It could be either one. We don't know.
Yeah.
But it's still useful information for people. We can also tell you stuff like, we can do basically primitive versions of shrinking, right? So like, are we able to find the bug without ever doing fault injection? Are we able to find the bug without ever using feature X or feature Y? Like, how much of your system can we turn off and we still find the bug? Often that can give you some guidance as well to like, what components are likely to be affected, which might affect your assignment of priority to it.
Interesting. That definitely seems very helpful, talking about the real world scenarios. What are the systems that you would say that are not very suitable for deterministic simulation testing and something like Antithesis?
Yeah, I would say, I think the thing that you brought up was actually probably the single biggest qualifier, right? Like, if you rely on vast amounts of third-party APIs, which you cannot run yourself, but would have to mock out in some way, I think that can be a big obstacle for people. Reliance on exotic hardware can make things challenging, right? Like, some hardware you can actually just simulate, right? Like, if I want to test a phone app or something, right? I can take the iPhone simulator and I can run it inside the hypervisor. Now I'm testing a phone app. Great.
Yeah.
Like, but there's things that aren't quite that straightforward. If you need, to simulate some code running on an ASIC or something, that might be a bit of a heavier lift to test in this fashion. I think if your system, the closer your system is to like an extremely CPU intensive straight line code without a lot of branching or a lot of possible different things it could do, the worse fit it is for this kind of system. Like, imagine a ridiculous situation, right? Imagine I have a piece of code which accepts 1 byte of input from you and then like spends half an hour, mining Bitcoin, and then like gets another byte of input from you and then does another half hour mining Bitcoin, right? Like I cannot explore that tree very effectively. It's going to take me half an hour to get to each, and I can't fast forward either because it's using 100% CPU, right? So like, that's going to be a very, very hard system to test in this style, because it really does depend on being able to run the system quickly in many different configurations and possibilities.
Interesting. So variety of use cases is one, like a thumb rule, like how many paths you can explore within your code base, and that makes it a good fit for something like Antithesis, right?
Yeah, that's right. And also, like, you know, how hard is it to test in a different way, right?
Yeah.
Like, if my software can do 5 things and it can only ever do 5 things, and I know what those 5 things are, I should just write 5 unit tests. Like, like obviously, right? Like,
Yeah.
but the farther away you get from that, then I think the more useful an approach like this one gets.
Yeah. So the more unknowns you have, the more likely you would need something like Antithesis, right?
Yes, that's right.
Awesome. Cool. What's coming up in the future?
Oh man, we have so many plans. We're doing some very cool stuff. So, like, I'm going to speak in slightly vague terms so as not to spoil an upcoming product launch. Many of our customers have asked us the question. Antithesis is very good at finding my bugs. Very, very good at finding them. And then once I found them, now I just feel bad, man, because like now I need to fix this bug. How can I fix it? So we are working on something to help you with that problem. We are working on something that will help you to fix the bugs after we find them. I think it will be pretty cool. And then the other thing, big picture thing that we're working on is taking everything I've described is especially useful in distributed systems, but we do believe it's useful in many, many, many other kinds of software development as well. So we are thinking very hard about how to generalize this approach to other kinds of systems, other kinds of testing for very different sorts of properties. And I think we'll have some cool stuff to talk about there too.
Awesome. Thanks a lot for joining me today and sharing all the amazing insights. It has blew my mind multiple times and I'm more excited to learn and read more on Antithesis and general techniques that you have shared. And yeah, so for our viewers, if you like this episode, please don't forget to check out Antithesis and subscribe to the channel because it helps me a lot creating more episodes like this. So thanks, Will. I'm looking forward to collaborating more on the same topics with upcoming features.
Awesome. Thank you so much for having me. This was really fun.